So we can proceed. So we have here problem solving on test of hypothesis on a single mean. This time the variance is unknown. So here's the problem. The Edison Electric Institute has published figures on the number of kilowatt hours used annually by various home appliances. It is claimed that a vacuum cleaner uses an average of 36 kilowatt hours per year. If a random sample of 12 homes included in a planned study indicates that vacuum cleaners use an average of 42 kilowatt hours per year, with a standard deviation of 11 kilowatt hours, does this suggest, at the 0.05 level of significance, that vacuum cleaners use an average less than 46 kilowatt hours annually? Assume the population of kilowatt hours to be normal, meaning normally distributed. So let's see. Let's analyze. So given, the claim is that the mean is equals with the mean of the population is equals to 46 kilowatt hour per year. So this is mu sub 0. Okay? This is the claim. Mu equals to 46 kilowatt hour per year. Okay? So how did we arrive at that? So because of the statement, it is claimed that the vacuum cleaner uses an average of 46 kilowatt hours per year. So this is believed to be true. Now let us test this claim. Okay? So that we can decide if we will reject it or not. No. So in that case, a random sample of 12 homes is considered. No. So therefore n is equals to 12. And considering those 12 homes with vacuum cleaners, no, the average kilowatt hour per year is 42. No, we have 42 kilowatt hours per year. Okay, considering 12 homes with vacuum cleaners. Okay, now is 42 kilowatt hour per year significant for us to reject mu equals to 46 kilowatt hour per year? So let's see. So use an average, okay, with the standard deviation of 11.9 kilowatt hours. So this is the standard deviation of the sample. Okay, use an average of 42 kilowatt hours per year with the standard deviation of 11.9 kilowatt hours. Okay, so the interpretation to that is it is the standard deviation of the sample and not the population. That's why we use lowercase s for the standard deviation value, 11.9 kilowatt hour per year. Okay. So does this suggest at the 0.05 level of significance? So alpha is equals to 0.05. Okay, that vacuum cleaners use an average less than 46 kilowatt hours annually. So from here, we have less than 46 kilowatt hours annually. So we're going to use one-tailed test. No? So we have one-tailed test for our hypothesis testing now because it is unidirectional. All kilowatt hours, no, less than 46 kilowatt hours. No? So assume the population of kilowatt hours to be normal. Okay, so the population of kilowatt hours is normally distributed. Okay, so it has a normal distribution. the population of kilowatt hours. All right, so let's analyze. So the assumption is normally distributed kilowatt hour population. Because of the statement, assume the population of kilowatt hours to be normal. Solution. So this will now be the null hypothesis. Mu equals to 46 kilowatt hour per year. That is believed to be true. This is the alternative hypothesis that the mean is less than 46 kilowatt hour per year. Because in the problem, this was mentioned less than 46 kilowatt hour per year. No? Then in the problem, there is the indicated level of significance, which is 0.05. So let us establish a critical region for our test statistic. So we're gonna use t-test, no? Or should I say, yes, t-test, no? So when we have t-test, this is the graph of the t distribution, no? The graph of the t distribution, similar to the normal distribution. Okay? So as you notice, mu less than 46 kilowatt hour per year, denoting that we will have one-tailed deaths. And since it is less than 46, it is a region to the left. A region to the left. Okay? This will now be the critical region. Region to the left is our critical region. And we have to determine the critical value of t here. T sub alpha. Okay? We are to determine, or should I say negative t sub alpha. No? Negative t sub alpha. So we shall determine that value. So negative t sub alpha, that is an alpha equals to 0.05 because it's one-tailed. Then in determining the t value, okay, so we can use table 8.8.8.4. Okay, we can use table 8.4 to determine the t value, t sub alpha. Okay, so we have to consider the number of degrees of freedom. So because we have what is the value of n in our problem? I think 12. So we have n, 12 homes. Okay, so n is 12. So considering kilowatt hour per year of those vacuum cleaners for 12 homes. Okay, so n is 12. So therefore, the number of degrees of freedom is 11. Okay, 12 minus 1 is 11. And this will have now a value. Okay, the value is negative 1.796. So how did we arrive at that value? Negative 1.796. So let's see. So table 8.4. Okay, let's see 8.4. Okay, so this is table 8.4. And we have here Point zero. As you notice, this is area to the right. So if that is area to the right, no worries. This alpha 0.05, considering the symmetrical property of the graph, this alpha of 0.05 is also the same as this. So let's locate alpha of 0.05. So we have this. Then we shall consider the number of degrees of freedom, which is 11. So going down, so considering 11 degrees of freedom, 0.05. There you go, 11 degrees of freedom, 0.05, 1.796. That will be the value of T sub alpha. Okay. Now, since it is area, we consider area to the left. Okay, so we have negative T sub alpha here. Okay. So we just put a negative sign, negative 1.796. So this is positive 1.796. Okay. So there you go. All right. So the test statistic computed value will be this formula. So how did we arrive at that computed value? So let's see. So how did we arrive at that computed value? So we have here single mean. Test on a single mean. Test of hypothesis on a single mean, wherein the variance is unknown. If the variance is unknown and we are to test a hypothesis on a single mean, we shall employ t-test. No? So here's the hint. So let us see the table. Okay, here we go. Mu equals mu sub 0. So test on a single mean, wherein the standard deviation or variance is unknown. If it is unknown, we are going to use t-test. So this is the formula, finding t. And this is number of degrees of freedom formula. So in the problem, we have one tail test, that is mean mu less than or not equal, yes, not equal to mu sub 0, right? So let's see. So let's see. Mu not equal to mu sub 0. There, okay. Mu not equal to mu sub 0. Oh, sorry. Mu not, less than mu sub 0. Okay. Mu less than mu sub 0. So which is 4 to 6 kilowatt hour per year. Okay, that's it. So then this will be the critical region, t less than negative t sub alpha. So that will be the critical region. Area to the left of the graph, no? Okay, so we proceed. Okay, so we have that. All right, so we have t-test, then computed value of t. So we have now 42 minus mu sub 0, 46 kilowatt hour per year. Okay, considering 12 homes, we got 42 kilowatt hours per year. Now, this is believed to be true for all homes, for all vacuum cleaners in every home, no? So we have 46 kilowatt hour per year. No? Is this significant, 42 kilowatt hour per year, for us to reject 46 kilowatt hour per year that is believed to be true? So let's see. So the standard deviation, so in here, we shall use the standard deviation of the sample, no? Which is 11.9 kilowatt hour per year. Then we divide by the square root of those 12 homes. We shall get negative 1.16. So let's see whether it is in the critical region or not. Negative 1 point, it's not in the critical region, right? It is in the non-rejection region. So we can now conclude. So if it is not in the critical region, we shall not reject the null hypothesis. Okay? Since the computed value t equals negative 1.16 is not in the critical region, therefore null hypothesis is not rejected. Thus, vacuum cleaners use on average is not significantly less than 46 kilowatt hours annually. No? So that will be our conclusion. Vacuum cleaners use on average is not significantly less than 46 kilowatt hours annually. So that's it. So I hope you understand. So in here we have problem solving on test of hypothesis on two means, variances known. So we have here a manufacturer claims that the average tensile strength of thread A exceeds the average tensile strength of thread B by at least 12 kilograms. To test this claim, 50 pieces of each type of thread were tested under similar conditions. Type A thread had an average tensile strength of 86.7 kilograms with a standard deviation of 6.28 kilograms, while Type B thread had an average tensile strength of 77.8 kilograms with a standard deviation of 5.61 kilograms. Test the manufacturer's claim using a 0.05 level of significance. So let's see. So as you notice, test of hypothesis on two means. So we have here two means. Means of two populations. No? So means of two populations. Wherein variances are known. Okay? So the variance of each population, okay, is known. No? So what is given? So the claim. So how did we arrive at this notation? Mu subs A greater than or equal to mu sub B plus 12 kilogram. To test this claim, 50 pieces of each type of thread were tested under similar conditions. Uh, where can we have that? Test the manufacturer's claim. Where's the claim? Here. This is the claim. Manufacturer claims that the average tensile strength of thread A. So that is considering the population, right? Of thread A. Okay. So considering the population of thread A. So that is mu sub A exceeds the average tensile strength of thread B. So that means if for considering the word exceed, that is greater than, right? Because of the statement, because of this phrase at least, no? At least, so we are to have greater than or equal sign. Greater than or equal. Greater than or equal sign. Okay? Because of the phrase at least, no? So mu sub A, average tensile strength. Okay, take note, this is average tensile strength of thread A exceeds, greater than, or equal the average tensile strength of thread B, that is mu sub B, by at least 12 kilograms. So that is plus 12 kilograms. Okay, so that will be the interpretation. And then we have here 50 observations, okay, or should I say 50 pieces of each type of thread. So n sub A equals to n sub B equals to 50 were tested under similar conditions. So that is 50. Then x sub A bar equals to 86.7 kilogram. As stated, type A thread had an average tensile strength of 86.7 kilograms with a standard deviation of 6.28 kilograms. So here is 6.28 kilograms. Then we have x sub B bar equals to 77.8 kilograms. Okay, the standard deviation is 5.61 kilograms. So test the manufacturer's claim using alpha of 0.05 level of significance. Alright, so we have the claim. Considering the claim, we can rewrite mu sub A minus mu sub B greater than or equal to 12 kilograms. Right? So this is the new version of the claim. Okay, we rewrite it in this manner, no? So h sub 0, that is mu sub A minus mu sub B equals to 12 kilograms. This will be our null hypothesis. How did we arrive at this null hypothesis? Why is it equals? Why we use equal sign? Okay, let's see. A manufacturer claims that the average tensile strength of thread A exceeds the average tensile strength of thread B. So that is the claim of the manufacturer. That is already the alternative. No? This is already the alternative. Exceeds the average tensile strength of thread B. So for the null hypothesis, take note, we always use the equal sign for the null hypothesis. So that's why we have here mu sub A minus mu sub B equals to 12 kilograms. And our alternative hypothesis, okay, mu sub A minus mu sub B greater than or equal to 12 kilograms. So this is our alternative hypothesis. Alright? So we proceed. So alpha is 0.05 as stated in the problem. So let us establish the critical region. Recall for total number of observations. For thread A, we have 30. If it exceeds 30, for thread B, if it exceeds 30, mu A minus mu B is approximately normally distributed. In my previous discussion, I have introduced this. If n sub a and n sub b, or n sub 1 and n sub 2, okay, is greater than or equal to 30, or should I say both are greater than and equal to 30, mu sub a minus mu sub b, the difference of the two means, is approximately normally distributed. So therefore, if it is approximately normally distributed, we have the sample standard deviation for thread A approximately equal to the population standard deviation for thread A. Likewise, the sample standard deviation for thread B approximately equal to the population standard deviation for thread B. So this is now the graph. So we're going to use z-test now. So we have here. So how did we arrive at z-test? So let's see. So we have the problem. Test of hypothesis on two means. Variances known. Okay. So variances known. Actually, it is not directly indicated in the problem for the variances. What we have is the sample standard deviation, right? So then we had arrived at the conclusion that this is approximately equal to sigma sub A, approximately equal to sigma sub B, because both threads, both sample size exceeds 30. Okay, so in this case we have now this problem. We continue. Therefore, so this is z sub alpha. Okay, so this is z sub alpha. Now, how will we determine this? Z sub alpha? No? But before that, so test on two means. So this will be mu sub A minus mu sub B greater than or equal to 12 kilograms. So difference of two means, right? And in that case, let's see the table here. We have here, okay? Mu sub 1 minus mu sub 2 equals d sub 0. Okay? So this is difference of two means. We can rewrite this as mu sub 1 equals mu sub 2 plus d sub 0, right? So we have the difference of two means, wherein the standard deviation are known, sigma 1 and sigma 2. So in my example, sigma A and sigma B are known. So we will now use z-test, no? Okay, so this will be the formula for z. This will be the formula for the value of test statistic. Okay, and then in my example, so the alternative is what? What is the alternative hypothesis? Let's see. So the alternative hypothesis is mu sub A minus mu sub B greater than or equal to 12 kilograms. Okay, So we shall use this. Mu sub 1 minus mu sub 2 greater than d sub O. Okay? Mu sub 1 minus mu sub 2 equals to is greater than d sub 0. We will use that. So note, no? Again, I repeat. For a continuous probability distribution, greater than symbol is the same as greater than or equal sign symbol. Okay? That is in my previous discussion, I have discussed that in detail. That the greater than symbol is the same as the greater than or equal sign symbol if the distribution is continuous. No? If the probability distribution is continuous. Okay, so we proceed. So this, since this is the one we will consider, so this will be for the value of z obtained by using this formula. Then z sub alpha will be obtained using table 8.3. Okay, using table 8.3. So z greater than z sub alpha will be our critical region now. Okay, so we know that alpha is 0.05, denoting error to the right because of greater than symbol. No? So this is 0.95. Okay, the region that is not shaded. No? So what is z sub alpha? Using table 8.3, we will arrive with 1.645. Okay, so we have the test statistic computed value. Okay, we have here. So this is the formula that I have. This is the formula I have shown. I have shown in my previous discussion. No, so this will be the corresponding formula in terms of a and b. X sub a bar minus x sub b bar. Then d sub 0 is simply the difference of the two means, mu sub a and mu sub b. No? D sub 0 denoting difference of the two means, mu sub a minus mu sub b. No? So this is d sub 0. This is d sub 0. Okay? Which is mu sub a minus mu sub b sub 0. Okay? Alright, so we continue. So we have here 86.7. Let's see. 86.7, okay. For thread A, okay, and then for thread B, 77.8. Okay, then the difference is 12. Mu A minus mu B is 12. Alright, so what will be our answer? So negative 2.60. Okay, we'll arrive with negative 2.60. Now, what is 86.7 minus 77.8? That's about, so the difference of the two sample means versus the difference of the two population means 86.7 minus 77.8, 8.9. Okay, 8.9. So is 8.9 significant for us to reject 12? Is this significant for us to reject 12? Let us see. So we obtained negative 2.60. Let's see, negative 2.60. It is at the non-rejection region. Okay, it is in the non-rejection region. Therefore, we shall not reject the null hypothesis. Since the computed value z equals to negative 2.60 is not in the critical region, therefore null hypothesis is not rejected. Huh? Thus, the manufacturer claimed that the average tensile strength of thread A exceeds the average tensile strength of thread B by at least 12 kilograms is insignificant. Okay, so that is the claim of the manufacturer, but actually 8.9 is actually less than, right? 8.9 difference of 86.7 and 77.8 is actually less than and not greater than, right? It does not exceed. Okay, that's why this will be our conclusion. No? That's why we arrive at this conclusion. So we now continue. So we have here problem solving on test of hypothesis on two means. No? Unknown but equal variances. So we have this problem. So we have an experiment was performed to compare the abrasive wear of two different laminated materials. 12 pieces of material 1 were tested by exposing each piece to a machine measuring wear. 10 pieces of material 2 were similarly tested. In each case, the depth of wear was observed. The samples of material 1 gave an average coded wear of 85 units, with a sample standard deviation of 4, while the samples of material 2 gave an average of 81 with the sample standard deviation of 5. Can we conclude at the 0.05 level of significance that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units? Assume the populations to be approximately normal with equal variances. Alright, so let us answer the problem. Now, alright, so we have given n sub 1 equals to 12. Okay, this has something to do with sample 1. Okay, so we have here the total number of observations, 12 for sample 1. Okay, 12 pieces of material 1 were tested. Okay, and then for sample 2, okay, which is we have 10. Okay, we have 10 observations. No, okay, and then in each case the depth of wear was observed. So take note that for the depth of wear that was observed, okay, so the samples of material 1 gave an average coded wear of 85 units. So this is the mean, the sample mean, okay, for material 1. The samples of material 1 give an average coded wear of 85 units with the sample standard deviation of 4. Okay, so considering the 12 pieces of material 1, okay, so we have now the average coded wear of 85 units with the standard deviation of 4 for the sample. For sample 2, so we have 10 observations, no? 10 pieces of material 2. And in this case, while the samples of material 2 gave an average of 81, so 81 units with the sample standard deviation of 5. So this is the sample standard deviation. Okay, now can we conclude at the 0.05 level of significance? So the level of significance is 0.05. At this level of significance, can we conclude that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units? Okay, so that's the question, no? So can we conclude at the 0.05 level of significance that the abrasive wear of material 1, so meaning it refers to the population of the abrasive wear of material 1, no? So it exceeds that of material 2 by more than 2 units. So considering material 2, does it exceeds by 2 units? Okay, okay, so in this case, we're going to determine if it exceeds or not, okay, with the level of significance of 0.05. So let's see. So upon in analyzing our data, since we have here 85 and we have here 81, so what is the difference between the two? What is 85 minus 81? If we are to compare 85 minus 81, x sub 1 bar minus x sub 2 bar, we get 4 units, no? Now since we get 2 unit, we obtained 4 units. So can we now conclude at the 0.05 level of significance, no, that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units? Okay, so if we analyze this, okay, we have mu sub 1 minus mu sub 2 greater than 2 units. Okay, so with that, no, since in our sample, okay, for considering the difference of the two means, we get 4. The difference of the two population means, we get, is it greater than 2 now? If since we get 4 units, can we then conclude that the difference between the two population means is greater than 2 units at a 0.05 level of significance? Okay, can we conclude at 0.05 level of significance that mu sub 1 minus mu sub 2 is greater than 2 units, since we have x sub 1 bar minus x sub 2 bar equal to 4 units, considering the two samples, sample 1 and sample 2. So we will test, no? So we can conclude later if this will this will be this will be rejected or not. No, the claim will be rejected or not. So so here's the assumption based from the problem. Okay, population of depth of wear of both materials are approximately normal. Okay, so the depth of wear of both materials are approximately normal, meaning they have normal distribution, no, with equal variances. So with equal variances, meaning with equal population variances. Sigma 1 equals sigma 2. Okay? Or should I say sigma 1 squared equals sigma 2 squared. Likewise, they have equal standard deviations. No? Sigma 1 equals to sigma 2. Okay? So we continue. So solution to the problem. So mu sub 1 is greater than mu sub 2 plus 2 units. So this can be we can rewrite this as mu sub 1 minus mu sub 2 greater than 2 units. And we can now state our null hypothesis. Take note, when we construct the null hypothesis, we always use the equal sign. So in this case, greater than symbol will be replaced by the equal sign. Okay? So this is believed to be true in the population. No? Mu sub 1 minus mu sub 2 is equals to 2 units. And we are gonna test this claim that mu sub 1 minus mu sub 2 is equals to 2 units. No? So for the alternative hypothesis, mu sub 1 minus mu sub 2 is greater than 2 units. Okay? So we will test the hypothesis at 0.05 level of significance. We will test the null hypothesis at 0.05 level of significance. So let us establish the critical region of our test statistic. So our test statistic is T. Why we have t-tests? Why do we have t-tests? So let's analyze. So as you notice, no? So let us see the previous slide. We only consider 12 units for material 1 and 10 units for material 2. So that we can able to use z-test, we should have 30 or more, no? For both materials. Okay? So since it's below 30, 12 and 10, okay, so we're gonna use t-test, no? So we can verify that, no? By analyzing the table I have shown before. So let's see. So considering the table I have shown, so this is the table. Okay, so take note, mu sub 1 minus mu sub 2. Okay, x1 bar minus x2 bar, t sub 0, sigma 1 and sigma 2 known. But in the problem, sigma 1 and sigma 2 are unknown, right? Let's verify again. Sigma 1 and sigma 2 are unknown, or sigma 1 squared and sigma 2 squared are unknown. Unknown but equal variances as stated in the problem. So this problem has an unknown but equal variances for both materials, no? For both populations. So it is not indicated in the problem. But as stated in the problem, assume the populations to be approximately normal with equal variances. So unknown but equal variances. Okay, so if that's the case, what formula to consider? What formula to consider? So we're gonna consider this. So we cannot use mu sub 1 minus mu sub 2 equals to t sub 0. Okay, so this one, it seems that we can use this one. This is used when the two standard deviations or the two variances are equal but unknown. They are equal but unknown. So therefore, since we're testing the null hypothesis, which is mu sub 1 minus mu sub 2 equals to d sub 0, no? So mu sub 1 minus mu sub 2 equals to 2 units, right, in the problem. So, and then it is stated in the problem that they have equal variances or equal standard deviations. And it's not stated in the problem the value of those standard deviations, but it is um, they are said to be equal in the problem as stated, but the values are not indicated. If that's the case, we can now use the t formula for the test statistic t. Okay, so we're going to solve for the value of the test statistic t. Okay, so in this case, for the alternative hypothesis, uh, this is employed mu sub 1 minus mu sub 2 greater than d sub 0. Okay, so since in the problem it is asking at 0.05 level of significance, okay, can we conclude that mu sub 1 minus mu sub 2 is greater than 2 units? Okay, so that is stated in the problem, no? So in that case, we're gonna establish the critical region. We have t greater than t sub alpha. Okay, t greater than t sub alpha. Alright, so we're gonna construct the critical region with the graph. Okay, so meaning if the t value here exceeds the critical value of t, no, the critical value t, t is at alpha equal to 0.05, therefore we shall reject the null hypothesis that mu sub 1 minus mu sub 2 equals to t sub 0. Okay, and this is a one-tailed test. This is a one-tailed test. It's unidirectional, right? And knowing the considering the t value, as you notice, we have here x sub 1 bar minus x sub 2 bar minus t sub 0, which is mu 1 minus mu 2, no? And then over s sub p. Okay, s sub p here can be obtained by taking the square root of the sample variance s sub p squared. This sample variance, when we take the square root, becomes the sample standard deviation. Okay, so we will use this formula where we have v, the number of degrees of freedom. So to obtain the number of degrees of freedom, we simply add the number of observations for both samples, n sub 1 plus n sub 2, then we subtract it by 2. Okay, so let's do it, no? So let's go back to our problem. Okay, okay, so we have this. So then we have, so we will now use t statistic. So this is t sub alpha. Okay. So the critical region is t greater than t sub alpha. So this will be the critical region. Okay. So in this case, this is the probability, okay, that, so this is the probability that t is greater than t sub alpha. No, the random variable t is greater than t sub alpha, which is equals to alpha. No, which is equals to alpha. Okay, so we proceed. So we compute the total number of degrees of freedom. Okay, we have 12 for sample 1. We have 10 for sample 2 minus 2. We get 20. So then, using table 8.4, okay, we will use table 8.4. We will get the t-value, and we will get 1.725. Okay, so let's verify is if it is 1.725 or not. So in this case, we have uh, in this case we have table 8.4. So let's see. We have alpha of 0.05 with 20 degrees of freedom. With 20 degrees of freedom, and the t-value is alpha 0.05 with 20 degrees of freedom. We have 1.725. So we get this 1.725. Okay, so that's it. So after that, no, so we're gonna compute for the test statistic value. So we have this formula. Okay, so we have x sub 1 bar minus x sub 2 bar minus b sub 1 minus b sub 2 sub 0 over s sub p square root of 1 over n1 plus 1 over n2. Okay, so we have to determine s sub p by taking the square root of n sub 1 minus 1, s sub 1 squared plus n sub 2 minus 1, s sub 2 squared over n1 plus n2 minus 2. So this is the formula now. So we'll obtain an answer of what? So we have 4.478. So we have 4.478. Then we substitute the values. We get the final answer of t equals to 1.043. So that's the test statistic computed value. So we're gonna compare it to t sub alpha. So let's see. So this is t sub alpha. So 1.725. This is 1.043. So what can we conclude? It is look the t value, no, the computed test statistic value, no, is not in the critical region. Therefore, we shall not reject the null hypothesis. So we will not reject that mu1 minus mu2 equals to 2 units. No? So that's it. No? So since the computed value t equals to 1.043 is not in the critical region, therefore do not reject the null hypothesis. Thus, at the 0.05 level of significance, the abrasive wear of material 1 does not significantly exceeds that of material 2 by more than 2 units. So that will be our conclusion. No? So it's up to you on how to construct the conclusion. No? What is important is that the thought that counts. It's the thought that counts. No? Alright, so this time we are going to solve a problem involving two means with unknown and unequal variances. No? So the following data represent the running times of films produced by two motion picture companies. We have company 1 and company 2. So these are the times. Okay. So test the hypothesis that the average running time of films produced by company 2 exceeds the average running time of films produced by company 1 by 10 minutes against the one-sided alternative that the difference is less than 10 minutes. Use a zero point 0.1 level of significance and assume the distributions of times to be approximately normal with unequal variances. So let's analyze the problem. So given, so we're going to test, no, mu sub 2 equals to mu sub 1 plus 10 minutes. So this claim that mu sub 2 equals to mu sub 1 plus 10 minutes. So how did we arrive at that? So according to the problem, test the hypothesis that the average running time of films. So it refers to the population, no? Population of running time of films, no? So that the average running time of films, okay, produced by company 2. Okay, so we have this mu sub 2 exceeds the average running time of films produced by company 1 by 10 minutes. So this is the equation now from the statement, no? From this statement. So this will now be the corresponding equation. Okay, exceeds the average running time of films by company 1 by 10 minutes. Okay, so that is mu sub 2 equals to mu sub 1 plus 10 minutes against the one-sided alternative that the difference is less than 10 minutes. So we have the one-sided alternative that the difference is less than 10 minutes. So mu sub 2 minus mu sub 1 is less than 10 minutes. So we have that inequality. Okay? So use 0.1 level of significance and assume the distributions of times to be approximately normal with unequal variances. So approximately normal with unequal variances. So in the problem, the variances of the two populations, population 1 and population 2, are not indicated, right? So, and likewise, they are unequal according to the problem with unequal variances. So if that's the case, we're going to have a test statistic, no? That suits the problem. So let's see. So the assumption is that according to the problem, distributions of times are approximately normal with unequal variances. Okay? Distributions of times are approximately normal with unequal variances. So in that case, mu sub 1 squared, sigma sub 1 squared is not equal to sigma sub 2 squared. Unequal variances. Likewise, the standard deviation of each population is not equal, no? So the distributions of times are approximately normal with unequal variances. So we can now proceed. So this is now the null hypothesis. Okay, mu sub 2 minus mu sub 1 is equals to 10 minutes. Then we have the alternative. Mu sub 2 minus mu sub 1 is less than 10 minutes. Then the level of significance as stated in the problem is zero point 0.1. And we are to establish the critical region. So this is less than 10 minutes. So this is now the region. And this is negative t sub alpha. Okay. And this is alpha now equal to zero point 0.1. Area to the left. And so this is the formula for finding the number of degrees of freedom. So how did we arrive at that? No? So let's analyze. So as you notice, we have here, we're testing this null hypothesis. Mu sub 1 minus mu sub 2 is equals to d sub 0. And then there is standard deviations that are not equal. Sigma 1 is not equal to sigma 2. And unknown. So in our problem, the variances are unknown, right? Likewise, the standard deviations are unknown, okay? And they are not equal as stated in the problem. And we're going to test the null hypothesis. So in our problem, we're going to test mu sub 2 minus mu sub 1 equals to d sub 0. No? So we're going to test this. Mu sub 2 minus mu sub 1 equals to d sub 0. Okay? So therefore, this will now be considered. What is the alternative? Less than 10 minutes, right? So therefore, this will be revised. So this inequality will be revised for the alternative hypothesis. This is mu sub 2 minus mu sub 1 less than. So less than d sub 0. Less than 10 minutes, right? D sub 0 is 10 minutes. Okay? And then, uh, this will be used. Okay? T prime less than negative t sub alpha. So one tailed test. One tailed test. So we have one tailed test. So this is the formula for finding the number of degrees of freedom. This is the formula for finding the test statistic value t prime. Okay, so t prime. Okay, so let's see. So let's go back. Okay, so we have this formula. Alright, so then we will have an answer of 8.88 minutes. Okay, sorry. S of 1, 8.88 minutes. So how did we arrive with 8.88 minutes? It's not indicated in the problem, right? It's not indicated. So we're going to solve it. So let's go back to the previous slide, no? So this is the previous slide, and Okay, so we have company 1. So I already taught you on how to solve for the for the mean, finding the mean and standard deviation of these values, right? In my previous lecture, right? So we can now, so then I also taught you on how to use the calculator in finding the mean and the standard deviation of the sample. So let's just use the calculator. Okay, so let's have, so we have this. So we have mode statistics. So if you don't, so mode 3 for statistics. Okay, and then we have shift, shift 1, then 2 for data, insert the values for company 1. We have 102, we have 86, we have 98, we have 109, we have 92. That's it. We have 5. Press AC, shift 1 again. We have the let's press 4 for, so we have x as SX for the sample standard deviation. We have 4. Then will give us an answer of 8.88 minutes. There. The standard deviation, the sample standard deviation is 8.88 minutes. Okay? So we have here 8.88 minutes S sub 1. Alright? So how many observations do we have? Shift, shift 1, 4, press 1 for N. We have 5 observations for sample 1. And then for sample 2, shift 1, 2. Alright, so we have 30.22. How did we arrive with this value? So we have, let's have um the previous slide. Let's analyze. So we have 81, 165, 165, 97, 134, 92, 87, 114. Okay, that's it. Press AC, then shift 1, then 4, then 4 for the sample standard deviation. We get 30.22. We have 30.22 minutes. Okay, then for n sub 2 equals 7, shift 1, then 4, then 1. So we have 7. Okay, that's it. So we're done. Alright, so now we substitute, no? So we're going to solve for V. Okay, we're going to solve for V. So solving for V, we have 7.38. So we'll obtain 7.38. So let's use our calculator to arrive at that answer. So we have 7.38. How did we arrive at that? Okay, so mode mode 1, then we'll use this. So we have 8.88 squared. Okay, all over 5. Okay, plus 30.22 squared over 7, then squared. Okay, then we have 8.88, 8.88 squared over 5, then squared. Okay, all over 5 minus 1. Okay, so plus, so we have 30.22. Oops, as you notice, it's the limitation. We reached the limitation of the calculator. So what shall we do now? Alright, so let us first simplify the numerator. So let's evaluate the numerator first. Okay, so we have 8.88 squared. Okay, over 5. Okay, plus 30.22 squared over 7. Then we take square of it. Okay, let's evaluate. We have 21384.66. Okay, 21384.66. So 21384.66. So let's write 21384.66 over 21384.66. 21384.66. Okay, over. Then we solve for the denominator. 8.88 squared over 5. Okay, we take the square of it. Over 5 minus 1 plus 30.22 squared over 7 squared over 7 minus 1. So we have 2189.99. 2898.99, I mean. Okay. So we have 2898.99. 2898.99. So we divide 21384.66 divided by 2898.99. So we have 7.37, just 7.38. So we get 7.38. There, we have 7.38. Okay? So take note that we will round it down, no, to the nearest whole number. So we have 7.38, that is b equals to 7. Okay? We will round it down to the nearest whole number. Okay? So if you got 7.99, that will be b equals to 7. So round it down to the nearest whole number. Okay? So that's it. So we proceed. No? So then this is the t-value. So this will now be the t-value, negative 1.415. Okay? So we have v, we have alpha of 0.1. So using table 8.4, so using table 8.4, okay, using table 8.4. So v is 7, no? So using table 8.4, v is 7, alpha is 0.1, v is 7, alpha 0.1. It's not it's not here. Here we have it. V is 7, alpha is 0.1 or 0.10. V is 7, alpha is 0.10. 1.415. That's an area to the right, right? Area to the right. So by symmetry, this will become negative 1.415. Okay, so this will become negative 1.415. Okay, that's it, no? So we proceed. And then take note that this is d sub 0. Mu sub 2 minus mu sub 1 equals to 10 minutes. No? So test is statistic computed value. So we'll solve for t prime. Okay, so we have, so as you notice, x sub 1 minus x sub 2 bar, x sub 1 bar minus x sub 2 bar becomes x sub 2 bar minus x sub 1 bar. So our reference is our null hypothesis. No? So this is mu sub 2 minus mu sub 1. So it follows that, so 2 comes first before 1. No? So therefore, this is x sub 2 bar minus x sub 1 bar minus d sub 0. So s sub 1 becomes s sub 2, s sub 2 becomes s sub 1. N sub 1 becomes n sub 2, n sub 2 becomes n sub 1. And we'll get, so as you notice, no, it's not indicated in the problem, the mean of those five values, of those, the mean for the sample, it's not indicated in the problem. So we can able to find it, no? So what's the mean? So we have 102. So mode statistics, let's find the mean. So we have 102, 86, 98, 109, 92. Okay, shift 1, data, shift 1, 4, then the mean 2, sample mean x bar 2. We have 97.4 minutes. So that will be our answer, 97.4 minutes. On the other hand, so let's change this to 81, 165, 97, 134, 92, 87, and 114. So we have that, shift 1, then 4, then x bar, 110 minutes. So we get 110 minutes. Alright, so that's it. So then we will arrive with an answer of 0.215. Is 0.215 in the critical region? Let's see. Is it in the critical region? 0.215. It's not. It's not in the critical region. Okay. So we shall not reject the null hypothesis. No? We shall not reject the null hypothesis. It's not in the critical region. 0.215. Since the computed value t prime equals to 0.215 is not in the critical region, therefore do not reject the null hypothesis. Thus, at the zero point 0.1 level of significance, the average running time of films produced by company 2 minus the average running time of films produced by company 1 is not less than 10 minutes. So that will be our decision. Alright?